myself.
Okay.
I'm the new student who emailed you.
Oh, okay.
James.
No, well, could be, yeah. So yeah, just get caught up by Friday, and you'll have to meet with an LA to demonstrate all that stuff again.
Cool.
Right.
And also, could I meet with people within the CS center and then have them also report back to you?
Well, Lab 15.
Okay.
If you're going to the student research center, then you're not essentially but you can all get help. For most people. Yeah. Thanks.
Soft hands, my drug. You taste like home to me. Echoing, reverberating. I am now remembering your kisses a dream. Elations extreme. One step closer. I am one step closer to heaven. And now I'm never the same, never the same, girl, twice. Oh no, I'm never the same now, never the same, girl, twice. Not the same girl you loved last night. Mysterious chemistry. Someone's cooking in the kitchen. Elixir of the pearl, a luscious berry swirl. I'm losing some sleep. No company I'd rather keep. One step closer. I am one step closer to heaven. And now I'm never the same, never the same, girl, twice. Oh no, I'm never the same now, never the same, girl, twice. Not the same girl you loved last night.
Yeah. It saves your project. Okay, we're good.
Never the same, never the same, girl, twice. Oh no, I'm never the same now, never the same, girl, twice. Not the same girl you loved last night. Not the same girl you loved last night. Never.
All right, so picking up where we left off last time, we were talking about standard input and output. And this will finish up the basics, and then we'll move on to conditionals. But you also had exposure to this in your lab this week, where you did an interactive program where you were prompted for input, I think Great British Pounds or something like that. And you did it was done using scanf. Scanf is just the opposite of printf. Instead of printing something, we're scanning it from the standard input, but it's still in a format, right? We still use the same placeholders with the one exception. If you're going to read in a double value, you use %lf instead of f. And the reason that you do that here is because doubles are double the size; they're 64 bits, and so that LF is long for a long floating point number. If you just use a regular old F, you'll actually be reading in what's called a regular old float, which is only 32 bits, and then you'll get nonsense results out of it. When using scanf, always make sure that you're using the ampersand. Okay. So again, the example that we did here in class was this miles converter. where we prompted for the input using printf, and then we scanned for the input using %lf because we were reading in doubles, right? And then we read into miles. But remember that we left off this ampersand here. If you leave off the ampersand, GCC will warn you about that. All right. Hopefully the audio is working, but my internet's not working on that computer. Anyway, it will warn you that you're probably missing something here. Are you sure that's what you meant? And so I'm going to go ahead and put back in that ampersand, and we'll see that that warning goes away. Right? Remember that it's just a warning. Oftentimes you do want to make sure that you're taking care of all those warnings, because if you don't, right, okay, I'll ignore that warning. I'll go ahead and run the program. Go ahead and enter 10.5 miles. Is it going to give me sensible output? Let's find out. 0 miles is 0 kilometers. Well, that's true, but I entered in 10.5, right? It failed to read in the input because I forgot the ampersand here. For now, that's just magic. We'll discuss it later. Right? But otherwise, it takes whatever the person types, some button masher, mashes the keyboard, hits enter, and it places the value into whatever variable you put here after the ampersand. That way you can use it in a calculation or whatever you're using it for, and then you can finally output it over here. Right? Again, when you're using scanf, you just need to make sure that you're using that % sign. This is very, very limited and very, very brittle. We'll almost immediately get away from this, as you did in your lab yesterday. You had that program that did it interactively, and then you modified it so that you used what are called command line arguments, or non-interactive input. Because the vast majority of programs are not intended for the command line, for somebody to be sitting there mashing their keyboard and typing, right? The vast majority of programs are written to interface with other programs in order to automate a process. And so what you want to do is you want to write programs that interact with other programs. The way that you can do that is by using command line arguments, right? Command line from the command line. Sometimes we just shorten it to CLAs for short, command line arguments. And you provide them when you actually run the program. So for example, if I ran my program a.out here, and then after that I did a space, hello, space 10, space 3.5, I would actually be providing it 4 command line arguments. The first one is always going to be the executable file name. If I were to rename a.out to my awesome program, then that first command line argument would be changed to my awesome program instead of a.out. This is the actual first user provided command line argument, hello. This is the second, this is the third, right? So in this case, there are 4 command line arguments. The first one is always going to be the executable file name. Typically, that's going to be a.out. Remember, in the main, we have these 2 things, argc, or argc, and argv. Now it is time to understand what those things are. Argc is the count of the arguments. So let me copy this so I don't have to type it all. There we go. All right. There we go. Argc is arguments. Remember, command line arguments. And the C stands for the count of the number of the command line arguments. In this case, if I were to call this program with these 4 arguments, that would take on a value of 4. Argv is an array of those arguments. The V there stands for vector. Don't worry about that. Just know that it's just argv. All right. The first argument is, again, that's always the executable file name, is accessible by accessing it through argv sub 0. In computer science, we always begin counting at 0. We'll understand why later on. It's a memory offset, basically. But otherwise, when you're using arrays or in pretty much any programming language, you are always going to start counting at 0. The first one is at 0. The second one is at 1. The third one is at 2, etc., etc. Right? So the second argument, the first one actually provided by the user, is at argv sub 1. Then you can go from there. Argv sub 2, argv sub 3, etc., etc. Depends on how many arguments you give it. If I typed just a.out, then there would be only 1 command line arguments. And the second one would be inaccessible because it doesn't exist, etc. Right? So how do we go about processing these command line arguments? Right? CLAs themselves are strings. We'll talk about strings later. More on that later. But for now, we're just going to, we just want to convert them. We, for now, will want to convert them to integers and doubles, right? So to do that, like you did in your lab yesterday, you can convert an argument to an integer using a to I. What do you think that I stands for? Integer, right? So it's A. The A stands for alphanumeric. So an alphanumeric string to an integer. The one that you used yesterday was for doubles. What was it called? A to F. That stands for alphanumeric to a floating point number. Right? So what I want to do now is I want to go ahead and go with our example over here. I want to take this interactive program that reads in, say, 10.5 miles interactively, and I want to change it so that it's non-interactive, that it uses a bunch of command line arguments. All right? In fact, there's only one command line argument. So what I'm going to do is I'm going to go ahead and take those two, and I'm going to remove them. Now, if I were to hand this in at this point, that's dead code. That'd be points off. Don't leave that. We called it cruft, remember? Cruft Hall fills with garbage, and now you can't do anything with it. Take it out. I should just remove it entirely. But I'm going to leave it there because eventually I'm going to put this in your notes, and you'll want to remember what it would look like. Okay? So if I were to just run this program as is right now, GCC, does it do anything? Well, yeah, it says 0 miles is 0 kilometers. Why? Well, because we never actually read in these values. I want to do that now. So instead of prompting for the input and then scanning for the input, I will assume that you gave me that input via the command line arguments, via something like a.out 10.5 miles. Convert 10.5 miles into kilometers. Right? So I'm going to use A to F, or actually, let's say miles is equal to args, or argv of something. You tell me what that something is. So remember that the first one is always a dot out, right? That first one is 0 is always a dot out. So is that the number? If I just replaced it with 0, no, it's the second one at the first one. Okay, at number 1, argv of 1. Now remember that the thing on the right hand side is a string, and the thing on the left hand side is a double. Right? Those don't match. If I were to try to actually compile this right now, it would say incompatible types. You can't change a char star, which is a string, into a double. You can't convert those, right? So what do I do to convert this a dot out, or this this argv of 1 into a floating point number? It's not a to I. That would convert it to what? An integer. Let's find out if that works. Actually, it'll compile now, but when I run this, 10.5. 10 miles is equal to 16 and change. Why? Because it tried to treat this as an integer. When it treats it as an integer, what happens? That floating point number gets chopped off. We call that what again? Truncation, right? Just like you had to fix your program to, instead of multiplying by 1 divided by 2, which is 0 because of truncation, you had to change that to 0.5, right? Okay? All right, so there's a to I now. Let's change this to F. Come on, F, there we go. Let's compile it and let's rerun it now. 10.5 miles is equal to 16.89 something and change. Right? Now it's reading it incorrectly. What happens if we screw up? What happens if I gave it more command line arguments? Hello, how are you? Right? It's not going to matter in this case because more, we never actually do anything with argv of 2, argv of 3, argv of 4, right? What if I gave it bad command line arguments? 10.5. There we go. Is that a number? No. So what do you predict what's going to happen here? It might crash, but more likely it's just going to say 0. Why? Well, think of what the computer is doing. It's trying to parse this string out into a floating point number. The first thing that it sees is t. Is t any number that you've ever heard of? Nope. So it stops immediately and says, I'm done. What has it parsed so far? Nothing. So what is the numerical value of nothing? 0. And that's why we get 0 here. If I tried to do it like partially, 5 and then it'll probably actually work with 5. Right? Why? Because it sees 5, Then it gets to this T and says, I'm done. That's not a number. What have I read so far? I read 5. So there's where you get your 5. What happens if I don't give it a command line argument at all? Something even worse in this case. It crashes with what's called a segmentation fault. We'll understand this later on when we actually do some work with memory, but a segment is a segment of memory. My program is trying to access a section of memory that doesn't exist or that doesn't belong to me. The operating system detects that and says, no way am I letting that happen. Because if you can write a program to just willy-nilly like access any memory at all, you could access passwords. You could access cryptographic keys. You could access any information that you want. So since it doesn't belong to me, the operating system says, nope, I'm going to kill your program and cause a segmentation fault. And that's what's happening here. Right? What's happening is that argument doesn't exist. So it goes to a memory location that doesn't exist or that doesn't belong to me. And consequently, it gets killed. What are we going to do to prevent that? Right? What I'm going to do is I'm going to this is going to be like a dovetail into our next topic. I'm going to add a condition. Right? I'm going to add in plain English here, if the user does not provide one command line argument, ... quit on, like let's say tell them they are dumb, and then we'll exit on, quit the program on it. Quit them, the program on them. Okay? There's my outline. That's what I want in plain old English. Now let's go back and fix this so that it's actually C code, because this ain't compiling anytime soon here, right? So if the user does not provide at least one command line argument, remember there was argc and argv. There's argument count, space. There's argument vector. That's what we want to pay attention to here. Did they give me the correct number of command line arguments? In this case, is it 1 or is it 2? Careful. It's 2. Why? A dot out and then the number. So if the user does not provide one command line argument, if argc is not equal to 2, that's how you read that. We'll talk about that here in a second. Then I will tell them that they're dumb and quit on them. Right? So we'll be nicer about it though. We'll print, please enter or include a number next time, ... or there. We'll be very nice about it and even say please. Right? We won't tell them they're dumb. Right? All right, now how am I going to quit the program? We can exit with a status code. Okay, I'm going to exit the program, meaning that the rest of this program will not execute. It'll just immediately quit out of the program. Okay, this one right here, we'll talk about that later with error codes. That's an exit code saying that something went wrong. An error of type 1 occurred. We could, of course, put this into 2. An error of type 2 occurred. An error of type 3 occurred. Or no error occurred. In fact, somebody asked me about this last week. Why do we have that return 0 down here? It does the same thing, but 0 means no error. You got down to the end of your program successfully, great. Go ahead and exit out of the program with 0. What kind of error occurred? No error occurred. Right? It was all good. Those are the conventions that we'll get to. Okay? All right, let's go ahead and compile it. And let's run it again with 10.5 to make sure that we didn't screw anything up. It still gives us the answer from before. Let's go ahead and run it with no command line arguments now. Right? Just no 10.5. And we get that error message. Please include a number next time. Oh, okay. What if I gave it 10.5 and hello, world, how are you? Right? That's not equal to 2. They're giving, what, 6 or 7 command line arguments there. It'll end up with the same thing. Right? Even though we did give it a number, we could modify our message to say, provide only one argument that is a number, please. Right? And then be done with it. Right? This is called a conditional. Right? And this is what we're going to be doing next. Before we do that, though, let me go ahead and make sure that you've got a copy of this program if you really want it in the notes there. Remember that these notes get pushed out to GitHub every day or every few days, certainly every week. And I put the link to all of them in last week's retrospective. Okay. Otherwise, let's start talking about what that was. That's called a conditional. All right? So let me bring this up. basically, you're going to have to write programs that make decisions. We're not talking about human-centered decisions like, oh, that's the most beneficial thing, so let's do that, or I prefer ice cream, so let's go ahead and have that instead, right? We're talking about decisions that are rote. Basically, if this happens, then this has to happen. Otherwise, something else happens, right? Normally, programs will follow that linear control flow, top to bottom, left to right, right? It's just like English, right? You read top to bottom, left to right. But more complex programs need to make decisions. They need to do one thing or another. They need to do something or not do that something. Or they might have 5 choices, and we have to pick one of them, right? Sorry, not Java. I should not have that there. Sorry, I am off. Let me see. Yeah, this is the correct one. Sorry. Let me get rid. Oh no, this is. This is correct. Okay, I don't know why Java was in there. Anyway, C supports. Correct grammar now that that's gone. Basic if else, and if else if statements. So we're going to be making a decision. If some condition, then we'll do something, or we won't do it. If some condition, we'll do A, or we'll do B, if that's not the case, right? Et cetera, et cetera. Each one of these is based on some logical condition. A logical condition is a Boolean statement that is either true or false. There's no in between. There's not something like that's 1/2, or it might be true, or it might be false, or I don't know what it is. Maybe it's true, maybe it's false, who knows, right? These things are going to have concrete values when you actually program them in, right? These are either true or false, okay? Here's our first basic example, which is an if statement, okay? I closed off the code there. There we go. So this is not real code right here. This angled brackets with condition, we'll fill that in here later, right? So if the condition up there is true or evaluates to true, then anything inside this code block, beginning with an opening curly bracket and ending with a closing curly bracket, gets executed. If this condition is false, this code block will not be executed at all, and life will go on for the program, right? Normal linear control flow will continue after this curly bracket here. Let's look at an actual example. Let me get rid of that and go ahead and get rid of this stuff too. Right. So if some condition, we need that condition. So we're playing, I did Huskers Akron this morning. All right. What about volleyball? Who do they play on Friday? So who? Cal State or is Wright State? Not Wright State. Wright State. There we go. Wright State and Huskers? Okay. This is for volleyball, sorry. Remember, we're a volleyball school now, right? All right, so Huskers, suppose they score. Actually, this doesn't really work for volleyball, right? Because let's just go with one set, I guess. So suppose that they scored 25, and Wright State only got to 14 or something, right? So who won there, right? If the Husker score was greater than the Wright State score, then what condition do we have here for that set? Huskers win. Let's print that out. Huskers win that set. All right, there we go. All right. Let's go ahead and, this is called demo. There we go. Let's go ahead and compile that and run that. Well, did the Huskers win? 25 is strictly greater than 14, right? So, yes, the Huskers won that set. Right? What if it was reversed? We won't be as bad as 14. Let's go ahead and say 21, and then they edged us out to 25 there. Now who won? Wright State. Wright State won that set, but that's not reflected here. Because only if this is true will this get executed. Otherwise, normal control flow continues after that closing curly bracket there. Printf end of program. To prove it, I'll go ahead and print the end of the program at the end here, and you'll see that that didn't get printed. It just went on to the rest of the program. Okay? So our observation here is if the condition is true, the code block executes. If the condition is false, then the code block does not execute. All right? Regardless, linear control flow continues after that code block. Okay? We'll modify the example here in a second. Here's a more complex version of that. The more complex version has an else statement. So in here, the first one was an example of you do something or you don't do it. This is an example of where you do something or you do something else. In this case, if the condition is true, then statement A is executed. Otherwise, if it's false, then statement B is executed. Right? Again, if the condition is true, then statement A executes. If the condition is false, then statement B executes. These are mutually, I have to spell it right, exclusive conditions. Right? In other words, exactly one and only one of these will execute. Right? It's either statement A or it's statement B. It is not the case that they'll both execute. It is not the case that neither of them executes. One or the other. It's got to be, because it's an if-else condition here. Let's come back over here and put that into our or integrate that here. So if the Huskers score is greater than the right state score, then the Huskers win. I buy that. Otherwise, what's the other possibility here? The right state won that step. Right state. Right. Why do I keep doing that? R-I-G-H-T. Right? I'm pretty sure that's how you spell it. Anyway, let's go ahead and compile that again. Now remember, right state is 25. So is 21 strictly greater than 25? Nope. This ends up being false, and therefore we come down here and the else executes. Right state won that set, or win that set. Let me go ahead and put it back to something that's proper. I don't know, 12. Yeah. There we go. So what will happen in this case? Oh, wait, it should be 25. There we go. Come on. There. All right. Come on. It's slow today. That's why it's happening. There, Huskers won that set, or win that set. Okay? Is there another possibility? Yeah. What happens in a based on a tie? Well, you've got to go until somebody wins. But if they're both tied at 25, then something else happens here. If I were to compile it as is right now, would it be correct? What's it going to do? Let's walk through it. 25 and 25. Is 25 strictly greater than 25? Nope. So what ends up happening? Else gets printed. Right? And did right state really win that set? No. So what we need is something else. We need a more complex way of doing this. And this is going to be an if-else-if statement. If condition A is true, then block A will get executed. Otherwise, it'll go. If it's false, it'll fall through and start checking these other conditions. It'll next checks condition B, and if condition B is true, then it executes block B. Otherwise, if that's false, it goes on to the next condition and the next condition and the next condition. You can do as many as you want. If you find yourself doing 3, 4, 5, it's probably doing something wrong, and you might want to rethink what you're doing. Right? But sometimes it requires that many. If like your lab next week when you do tax evaluations, there are 7 brackets, and so you do need 7 of them. Right? All right, so let's come back over here and let's modify this. Right? I'm going to put in another condition here. That condition would be if the Husker score is strictly less than the right state score. Right? Now that will work, because if the Husker score is strictly greater than the right state score, then the Huskers win. If the Husker score is strictly less than the right state score, then right state won. What's the other possibility here? Printf. They tied, right? Tied. Need to get to match point. Right? There we go. Okay. Now again, 25 and 25, they're still tied after that match. Oh, you got to spell everything right. Huskers. There we go. Huskers. There we go. All right. And out. There. Tied. Need to get to match point. Okay. So we have an if-else condition here. And again, you can. I only had 2 conditions: condition A and condition B. You can put as many as you want. You can put as few as you want. Right. But this is what's called a full if-else-if condition, because there are multiple conditions there. Right. The order matters, right? The first condition that evaluates to true is the block that gets executed, and the only block that gets executed. All right? Executed. There we go. All of these blocks of code are mutually exclusive. Exactly one of them and only one of them will ever be executed. Right? Let's come back over here and observe that. Again, what if the Huskers win and they just blew them out? 4 there. Come on, 4. There we go. Right? What's it going to print in this case? Husker score is strictly greater than the Wright State score, so this gets executed. This is ignored, this is ignored. Right? In fact, this entire if statement is ignored. Only one of these things will ever execute if somehow we got blown out. Right? There we go. Wright State won. Right? Only one of these things gets executed. That's not right. So we'll go ahead and when we post this to the notes, let's hear. I'll go ahead and post this to notes right now. I will have the proper score in there. All right. I don't know. Do they even publish lines for volleyball games? Okay. All right. So generally, what you do is the approach here is generally when you write if conditions. You put the most specific condition first, and we'll do an exercise later that exemplifies that. Then you order them, the most general to the from the most specific to the most general, and that's because the else block, that's the most general of all. If none of these conditions evaluates to true, that's not true, that's not true, that's not true. This is the catch-all. That's what happens at the end if nothing else occurred. That one is the one that gets executed. So some style notes here. The way that I've done it is I've put the opening curly bracket in the same line as the if statement. Right? That's the modern way of doing it. If you want to go down to the next line, that's fine. Just be consistent about it. Note the white space. Each one of those blocks was indented because it's like a bullet pointed list. Bullet pointed list, then sub list is going to be indented. Right? Make sure that you are being consistent about it. The conditions are always put inside of the parentheses. Actually, that's not style, that's required. Let me show you what happens if you don't do that. I'm pretty sure that this will not compile because what are you talking about? Right? I can't look at a condition unless it's in the parentheses there. So this is actually syntactically required. So, there we go, required. Okay? All blocks of code are indented inside of the curly brackets. Also, one thing that you should understand is that the else block is always optional. Right? In fact, is there really a difference between an if condition and an if-else condition? The only difference is that we just chose not to have this condition right here. And in fact, another observation here is there really is no else-if condition at all in C. What is this? Else, and then it goes into another if statement, right? And so that's why we can write it like this, but really there's no such thing as an else if. Right? It's just syntactic sugar that we're putting these together here. Okay. All right. So there's style. We can do numeric comparisons like we've been doing, right? Comparisons. There we go. Okay. You have the basic, strictly less than, right? That is strictly less than. That's on your keyboard. You can find it. It's down below, right next to the M. You also have the strictly greater than, and that is right next to it, strictly greater than, right? But try as you might, can you find anything that looks like this? Less than or equal to, or greater than or equal to? Are those anywhere? Those are used in math, certainly, right? And the way that I've depicted them here, that's how you would do it in math. But do you search as you might? Is there anywhere on that keyboard that has those? Nope. So as a consequence, we have to use something else. We have to approximate it. Less than or equal to. Well, it's just like you read it. Less than or equal to. Right? Greater than or equal to. Again, greater than or equal to. And that's how you have to get it. Don't, it's not a greater than. There we go. Not the following. It's equal to or less than, or it's equal to or greater than. That's a little smiley guy there that's really sad. And that one is an arrow. Neither one of those are recognized in any language that I know of, except for the arrow that is recognized in PHP. Right? So not those things. Write it as you would read it. Less than or equal to, greater than or equal to. You have strictly equal. Right? So in this case, if this were algebra, I'd be putting a one equal sign. But we already have a meaning for that. What is the meaning of one equal sign? That's the assignment operator. Take the thing on the right-hand side and put it into the variable on the left-hand side. And so consequently, we just have to add another one. Two equal signs, right? So two equals signs. There are some languages where there are different types of equality. And you've got a strict equality and a loose equality. And one of them is two equal signs, and the other is three equal signs. We don't have that in C, though. Would be like in PHP if you did A. That's the loose equality. And what this would be is if it were 2 is equal to the string equals 2. That distractor, that's not in this language at all, right? That would be, yeah, forget about it, because otherwise you'd have to do this. Equals equals equals. Now that's false, because one of them is a string and one of them is an integer. Right? But not in C. Don't worry about it. Right? You have inequality. Now try as you might, you're not going to find this on your keyboard either. Not equal. There we go. Right? It's just an equal sign with a slash through it. So what looks kind of like it? An exclamation point followed by an equal sign. Not equals, right? Because we can't type, mathematical symbols very easily. Okay? So there's an inequality. All operators operate on two operands, that is values, right? Operands can be, that is the left-hand side or right-hand side, can be values, say, for example, 5 or 3.4 or something like that, or numbers, right? Actually, that is literals, or expressions, right? Or variables, or a combination of all of them. Okay? So, for example, let's come over here, and I already put this into the notes so we can get rid of it. Do you remember some of the symbols that we wrote? Like, what was this one? Root 1 is equal to, what is it going to be? Negative b plus square root of b squared minus, or b squared, minus 4 times a times c, all over 2a. Remind me, first of all, am I writing it correctly as is? No. What has to happen? Yep, this has to be in the numerator, and this has to be in the denominator. There we go. That's correct. Did I do everything else correct? I think so. B squared minus 4ac, there we go. And root 2. There we go. 2, there we go. And that's going to be the minus 1. Okay? Let's just go ahead and give these values. Double A is equal to, 10. B is equal to 20. C is equal to 30. You can go ahead and create multiple variables on the same line. You can assign them all on the same line if you want to. If you want to, you can go ahead and make this into multiple lines. Double and double. Right? The first version I just saved on a little bit of typing. Okay? What should be the value of this? I don't know. Let's ask Wolfram Alpha. Right? Roots of what did I say? 10x squared plus 20b x plus 30. Right, what should they be? Come on. All right. Well, okay. What does that I tell you about? It's going to be what? Imaginary, right? Let's find out what happens here when we don't have any proper checks. Printf, roots are, %f is the placeholder for floating point number, and %f, and the line. I'm going to print out root 1 and root 2. So GCC demo. Oops, I need to declare those things. So double and double. There we go. All right. Oh, and what else do I need to do if I'm going to use the square root? It's part of the math library, but what do I need to do at the command line? Flag, what is that flag? LM. You're going to need that possibly that you're going to need that tomorrow in your hack. Why? Because you're going to be doing math stuff. Right? You're going to be calling cosine and sine and square root and a bunch of stuff. So remember hyphen LM. All right, let's go ahead and run it. Nan and nan. Why am I getting nans? What does nan stand for again? Not a number. Because it cannot handle complex roots like this. Okay. So, what are we going to do here? Let's add a condition. If. How do I know that I'm going to have a complex root here? What values are relevant here? Trying to, it comes up with a complex number, an imaginary number. Why? Because the square root is negative. So if this value right here is negative, it's less than 0, I'm going to have a problem. Let's go ahead and say, I'm going to print out a problem. I cannot handle complex, that is, imaginary roots. And we can quit on them if you want. Exit 1. There we go. We'll quit on them. All right, let's go ahead and try to compile that again. And I cannot handle imaginary roots. Right. Go to Wolfram Alpha. Right. But there is an if condition. There is a much more complex condition there. This entire thing over here is a combination of expressions, variables, and what are called literals. B is a variable. B times B is an expression. Subtraction is an expression. 4 is just a number. That's called a literal, right? And then A and C. And then we're asking, is that less than 0? And if it is, then we'll just exit with an error message here. All right, so give me something that will work. We just need to make B very, very large, right? All right, so let's go ahead and make it huge. Right? There we go. And now it'll work. Is that correct, by the way? How would I know? I could pull out my calculator, or I could let Wolfram Alpha do it for me. 10, 230. And what are those values? Come on. All right, double click on it, and you get negative 19.8. Negative 19.8, that's good enough for me. You'd have to click back, click on the other one to see what the other root was. That one right there is negative 0.15 and negative 0.15. Right? So I think that this program works so far. But the left-hand side was a complex expression. Okay. What else could happen here, by the way? Yeah, this specific, or in any quadratic equation. Yeah, well, what's equal?
Where the square root of b squared minus 4ac.
Oh, that would be fine. Taking the square root of 0 is 0. That's okay. A could be, what if A is 0? Yeah, what it's like something, x over 0. Can you divide by 0? Nope. So let's add another condition here. Else if A is equal to 0, then I'll go ahead and copy and paste this, but I cannot handle what? What does that mean in this case, that A is 0? Let's come back over here. Yeah, if A is 0, then that means that this thing goes away. Is that a quadratic equation? No, right? So that's a linear equation. So I cannot handle linear equations. Try again. All right, there we go. Why did I put it in an else if? I want to quit if this happens, right? Am I ever going to get down here? No, I want to make them mutually exclusive. I don't want 2 error messages, potentially. I want 1 error message or no error message and success. Okay? Let's see if it works, though. Got to test it. There, I cannot handle linear equations. Try again. All right. All right, good. Let's see. Anything else? All right. Let's do some more down here. What if you wanted to check this? Oh, yeah, go ahead.
Is exclamation point G just do your last?
Yeah, oh, so yeah, if you ever see me doing quick keys or anything, go ahead and ask me about it. Remember that you can always use up arrow keys, down arrow keys to scroll through your entire history. So that if you don't want to type out GCC demo-LM again, just go ahead and hit up until you get to where you want, and then hit it. This is called a bang. We call it the exclamation point a bang. And so if you just go G, it executes the last command that began with a G. I don't know what's in my history here. Like if do I have something that starts with an S? Uh-oh. All right. There we go. The last thing I did was install a curl library, and that began with sudo. You'll do that eventually in like lab 9. Right. All right. Let's go ahead and clear that out. All right. So, yes, there's some quick keys there. What else? If I think of any more, if you see me doing any more magic, let me know. All right. But that's another way that you can avoid. Oh, another one would be, I'm doing it for the first time. What's it called? Demo. D, and then tab over, and it'll automatically complete it for you. Right? There we go. And then, of course, you need the -lm. Right. Okay. Or more over here. All right. So you can, but shouldn't, do the following. Right. So if A is equal to, say, A, there we go. Why should you never do that? It's always going to be true. This is what's called a tautology, right? It is something that is always true. Don't write this code, right? If you want to do something in the event that A is equal to A, then just do it, because no matter what, this block will execute, right? You also wouldn't do something like this if 0 is less than 10, right? This is also always true. Something that's the opposite of that would be if if 0 is not equal to 10, right? No, this one there. So there, that's what I wanted. What is the relationship between 0 and 10? Will they ever be equal? Nope. This is dead code. 0 is equal, or 0 equals 10 is a contradiction. It can never be true. It is never true. Always false. And so this is dead code. This will never actually execute. Printf, hello. All right. If I run this, no matter what, that will never print it again. No, actually, I'm exiting, right? So let me go ahead and fix this so that it's 10 again. There we go. And that never actually gets printed. Right? In fact, I'm surprised that the GCC is not warning me about this. I'll talk about this here in a second. Nope. All right, so it's not warning me about that. But certainly it's probably optimizing it so that this code gets thrown away entirely. Right? Because it immediately sees, no, that's a contradiction. This is dead code. I'm going to go compile that away. Right? If you compare a variable to a value, write the following. If A is equal to 10, then print F, A is 10. This is correct, just like we did above. It is still correct, but bad style to reverse it. So for example, if 10 is equal to A, right? Would anybody actually want to read it like that in English? No. So if you're comparing the contents of a variable to a number, the variable comes first and then the number comes second, right? This will, A is 10, right? Because I set it equal to 10. So both of these will execute correctly. A is 10, A is 10. But this one is stylistically worse, right? The first one is how you would do it. Okay? All right. And there are exceptions to that, of course, right? Here's another one, another falsy one, right? This will never execute. Why? Right. Oops. So, will A never be equal to A? No, it's just the opposite, right? Huh? So, don't do that, right? Write good code, okay? All right. Last thing today is going to be our first pitfall, right? You cannot, period, cannot use numerical comparison operators for strings. Basically what you're doing is you are comparing memory addresses when you do that. So for example, let me just go ahead and give you a preview of what strings look like. Char name is equal to Chris. There I am. Right? If the name is equal to Chris, then say, hello, Chris. Right, there we go. Now is that going to execute or not? Chris is equal to Chris, right? Let me put an else. Else. Printf. Hello, Bob. Alright. Which one is it going to print? Hello, Chris, or hello, Bob? Let's find out. Hello, Bob. This does not work for strings. The reason is this right here, this name is being stored in a memory location. Let's call it ABC. This other Chris right here is also being stored in a memory location. Let's call it XYZ. ABC, XYZ, those are not the same memory locations. They're in completely different parts of the computer. So when it goes to make the comparison here, it says, is that memory location the same thing as that memory location? And of course they're not, because it's different memory. Right? So consequently, it goes with Bob. Yeah.
We just point Chris's to ABC.
The solution here eventually is going to be to use a strcmp, which is string comparison, and it'll compare the contents of strings. There's another question or answered? Okay. All right, so you cannot use numerical in fact, you could do this. Is my name less than Chris? First of all, what does that even mean? We'll talk about that when we actually get to strings. But no, this will not, less than or equal to is what we would probably want, right? GCC. All right, now it's super slow. Come on, there we go. And it still prints out Bob. We'll pick it up there on Friday.